just want to welcome you. My name is Molly Anderson, and this is the first lecture of this summer's Geschke lecture series. And since 2005, this series has been bringing thought leaders to this island, and it wouldn't have happened without the real generosity of Nan and Chuck Geschke. And I'd like just to take a moment to thank them. I have one announcement about the next Geschke lecture series. It was to be held next Monday, and the topic was Jerusalem, then and now. And Dr. Alterman unfortunately lost his mother today, and so he won't be able to come to Nantucket. But we talked today, and he has promised to come and give the very same presentation next summer. So we'll look forward to that. And now I would like to ask Chuck Geschke to come and introduce us to tonight's speaker.
Well, thank you, Molly, and it's a pleasure to be here and a pleasure to have the opportunity to welcome all of you to, as Molly said, the first Geschke lecture of the summer of 2018. It's my pleasure tonight and my honor, really, to have the opportunity of introducing the first lecturer of the season, Dr. John Holdren.
Speak into the microphone, please.
All right, you know what I'm going to do? I'm going to bring the microphone to me. Thank you for pointing it out. Dr. Holdren has had an outstanding career in both government and academia. From 2009 through 2017, he was the senior advisor to President Barack Obama as the assistant to the president for science and technology. Dr. Holdren was previously the Teresa and John Hines Professor of Environmental Policy at the Kennedy School of Government at Harvard University. Also the director of the Science and Technology and Public Policy Program at the school's Belfer Center for Science and International Affairs, as well as the director of the Woods Hole Research Center on the Cape. Dr. Holdren taught at Harvard for 13 years and at UC Berkeley for more than 2 decades. His work has focused on the cause and consequences of global environmental change. Population control, as well as energy technologies and policies and ways to reduce the danger and technology policy and reduce the damage from nuclear weapons and materials and science and technology policy. He has also taken measures to contextualize the United States' current energy challenge, noting the role that nuclear energy could possibly play. Dr. Holdren studied aeronautics and astronautics and plasma physics, earning a bachelor's degree from the Massachusetts Institute of Technology in 1965 and a PhD from Stanford University in 1970. Dr. Holdren is the author of over 200 articles and papers, and he has co-authored and edited some 20 books, each book length and book length reports. He has, he is the recipient of numerous awards and a member of the several honorary societies. It's my honor and pleasure to present to you this evening's lecturer, Dr. John Holdren.
Well, thank you very much, Dr. Geschke. It's a great privilege and an honor to be here. I am amazed and heartened by the size of the crowd. This is terrific that there's this level of interest in the climate change issue here on Nantucket. I want to mention that I'm accompanied here this evening by an all-star delegation from the Woods Hole Research Center. It's President and Director, Dr. Phil Duffy. You ought to stand up, Phil. Its Deputy Director, Dr. Max Holmes. And its Vice President, Allison Smart. I'm also accompanied by my wife, Dr. Cheryl Holdren. When I was the science advisor to the President of the United States, my wife was known as the science advisor's science advisor. Her PhD is in biology, and while mine is in physics, she kept me honest. I'm going to try to cover a lot of ground tonight. I may go a little quickly. I tend to use wordy PowerPoints because they can stand alone as an account of the talk for people who couldn't come. And for those for whom some of the slides go by too quickly, we will post this presentation on the Woods Hole Research Center website, www.whrc.org. So starting with what I call the essence of the energy climate challenge, I put it this way: without energy, there is no economy. Without climate, there is no environment. And without both, without economy and environment, there's no material well-being, there's no civil society, there's no personal or national security. And the essence of the challenge is that for a very long time, the world has been getting most of the energy that its economies need in ways that are seriously disrupting the climate that its environment needs. We start with a little terminology. Global warming, which is the most frequently used term for what has been going on, is actually a misnomer. The term global warming implies something that's uniform, global, across the planet, that's mainly about temperature, warming, that's gradual, warming, not heating, for example, and it gives the impression that it's quite possibly benign. What could a little warming do that we should worry about? But what's actually happening is highly non-uniform, and we'll see that. It's not just about temperature, it's about all the factors that make up weather. It's rapid, not slow, but rapid compared to the capacities for adjustment, both in society and in ecosystems. And it's harmful for most places and times. There's some places for some period of time that may get some benefit from climate change. But for most places and most times, and certainly all the more, the further out we go and the larger the disruption, it becomes harmful everywhere. A more descriptive term than global warming would be global climate disruption. Unfortunately, that's a mouthful. I've been trying to propagate that for 2 decades now with an utter lack of success, but I insist that it is a better term than global warming for the reasons indicated here. It's also important to understand the relation between climate and weather. Climate is the pattern that the weather exhibits for a particular region and a particular season or for the whole year. It's expressed as average values, typical highs and lows, and extremes of all the main weather variables, not just temperature, but humidity, rain, snow, and winds. And it's defined over a period of decades. That is, what are the averages, the extremes, the highs and lows observed over a period of decades? That's what constitutes climate. And how climate is changing over time is most frequently expressed quite simply as the change in the year-round average air temperature for a region or for the globe. And what one needs to understand, why does this, suddenly my control has gone away. That is really weird. Let's see. It's humidity. Thank you. There we go. Small changes in that index, that average surface temperature, typically reflect much bigger changes in the aspects of weather patterns that matter the most to humans and ecosystems. Most importantly, when the average temperature changes a little, the frequency and magnitude of the extremes, not only the extremes of temperature, but the other variables of humidity, of precipitation, of winds and storms, all of those things at the extremes change a lot. And we'll see more in a few minutes about exactly how that happens. But it's a little bit like the temperature of your body. You know, when your body temperature goes up, say, 2 degrees Celsius, 3.6 degrees Fahrenheit, you know that that is telling you something is amiss in the complex underlying system that is your body. And similarly, in the case of climate, there's a very complex underlying system, and a little bit of change in that one index, the average temperature, is telling you that something is amiss in that system. So in the rest of this talk, I'm going to do a couple of things. I'm going to talk more precisely about what we know and how we know it, about the pace and the character and the causes of climate change. I'm going to talk about the ongoing impacts on people and ecosystems. I'm going to talk about what we expect, that is, the future of climate change and its impacts. And I'll provide some examples from the Cape and Islands. And I'll talk finally about what we can do, reducing emissions, how much, how fast, what we can do to adapt to unavoidable changes in climate, changes we can no longer stop, which is a matter of acting locally. I'll talk for the need for and current lack of federal leadership in this domain. And I'll talk about what states, cities, businesses, civil society organizations, and citizens can do to help address this challenge. So let me start with what we know, and I like this quote from Daniel Patrick Moynihan: "Everyone is entitled to his own opinion, but not his own facts." So what we know that rapid warming is ongoing. 2016 was the hottest year in more than 130 years of good temperature records. 2017 was the second hottest, 2015 the third, 2014 the fourth. Every decade since the 1960s has been warmer than the last. In fact, the Earth has been warming more or less steadily for the last 100 plus years as the increasing influence of human activities has come to dominate the natural variability in climate. It's uneven. As I said before, the Arctic, the West Antarctic Peninsula, and the mid-continents are warming much faster than the global average. This is the annual average temperature anomaly in the hottest year on record, 2016, January through December. The average for the globe was about 1 degree Celsius above the 1951 to 1980 average. And you see, you look what happened in the Arctic. Instead of 1 degree, which was the global average, you have 2 to 4 degrees Celsius was what happened in the Arctic. Similarly for parts of the West Antarctic Peninsula, and the typical increase in the mid-continents was 1 to 2 degrees. The sea ice in the Arctic, this is floating ice, has been shrinking rapidly. This is a plot of the period since satellite observations began and gave us a good indication of the coverage of sea ice in the Arctic. As indicated here, sea ice floats, so when it shrinks, it doesn't change sea level. This is not one of the causes of rising sea level. But the change from ice to open water, when the ice shrinks, has drastic effects on regional temperatures, on winds, on storm impacts, and on valued species. And we know that the recent pace of sea ice decline is something that is unprecedented for at least the last 500 years. Greenland is steadily losing its land ice, and loss of ice from the great land ice sheets, Greenland and Antarctica, and from the glaciers, does contribute to sea level rise. This shows what has happened to the mass of ice on Greenland just since 2002. And you can see it just steadily falling. It's losing an average of 280 billion tons a year of ice into the ocean. It's now clear, it wasn't really clear 10 years ago, but it's clear now that Antarctica as a whole is also losing ice. is losing ice at an average of about 130 billion tons of ice per year. The pace of sea level rise, not surprisingly, has gone up. That results from the ice additions, but also from thermal expansion. When ocean water gets warmer, it expands. So that contributes to sea level rise. And in addition, groundwater depletion. Around the world, we are pumping groundwater faster than it's being replenished. That groundwater, largely used for irrigation, runs off into the ocean, and it adds to sea level rise. Next point, humans are without doubt the main cause of current climate change. We know that for a number of reasons. The rapidly rising use of fossil fuels that started around 1750 and has been augmented by land use change, which also adds carbon dioxide to the atmosphere, produced a pace of increase in the atmospheric concentrations of carbon dioxide, methane, and nitrous oxide, the most important heat-trapping gases, that is unprecedented in Earth's history. We've never seen, and we can look back now for hundreds of thousands of years with various indicators, including bubbles trapped in ice cores in the Antarctic ice, and figure out what happened over these hundreds of thousands of years. The concentrations of these gases have never risen as fast as they have in the industrial era. In addition, the human agency is scientifically absolutely established. There is no natural explanation for those rises, and they fit perfectly what we know about the history of fossil fuel use and of land use change. And when the effects of the buildup of atmospheric particles in parallel with this, also a form of pollution, which somewhat masks the warming effect because most of the atmospheric particles reflect sunlight and produce a cooling effect, which again partly masks the warming effect of the heat-trapping gases, the greenhouse gases. When you take that into account, the observed increases in carbon dioxide, methane, nitrous oxide, and hydrofluorocarbons explain essentially all of the observed increase in global average temperature over this period. And not just the magnitude, but also the spatial and temporal patterns of the warming match what basic physics and climate models both say should be the result of the observed buildups. And finally, there are natural influences on climate. We know that. The climate has been changing naturally for millions of years. We understand those influences pretty well, and we understand that under those natural influences, the Earth was cooling for about 6,500 years up to 1750, the beginning of the Industrial Revolution, and it would have continued to cool, leading toward another ice age, perhaps 10,000 years down the road, except we fixed that problem. Unfortunately, we overcompensated. We have not only ruled out and halted the cooling trend that was heading for another ice age, but we have switched it completely and put the world on a warming trajectory. What this slide shows, and again, I'm not going to spend a whole lot of time on it, but the nerds in the room might want to examine it in your abundant leisure. The bottom line here is that when measurement and analytical uncertainties are taken into account, essentially all of the recent observed warming is explained just by the human influences. The solar variability, the effect of volcanoes, internal variability, these little lines of basically centered around zero at the bottom are negligible compared to the human influences over this period. This is the period just 1950 to 2010. And this is the reversal of 6,500 years of natural cooling. This goes back to 12,000 years before the present, reconstruction of the surface temperature of the Earth. The scale here is the magnitude of the departure from the 1960 to 1990 average, and you see that for 6,500 years, up until the beginning of the Industrial Revolution, the Earth was cooling, and suddenly it's turned around and you see this spike at the end, astonishing spike, completely inconsistent and counter to the natural trend. Now, the next thing that we know is that climate change is already causing harm. This is not just a problem for our grandkids and our great-grandkids. Harm is already occurring in many forms and around the world. And you see the list here. I'm not going to read it to you or I'll run out of time, but you can read faster than I can talk in any case, and we'll provide some examples of these next. But all of these changes, the floods, the droughts, the wildfires, all the way down the list to changes in the distribution and abundance of valued species, they are all plausibly linked to climate change by theory, by models, and by observed fingerprints. And what the fingerprints mean is the pattern in which these changes are occurring. One of the most obvious ones is more heavy downpours, leading to more flooding. The reason this is obvious is that a warmer atmosphere can hold more moisture, and if there's more moisture up there at one time, more can come down at one time. And that's exactly what happens. You see all over the United States, this is the difference, the percentage increase in heavy downpours between 1958 and 2012. And you note, by the way, that by far the biggest increase was in the northeastern United States. Bigger downpours do mean more flooding. 100-year floods are now occurring once a decade or more in many places. In Houston, 3 500-year floods occurred in 3 years. That obviously calls into question of whether these are really any longer 500-year floods expected to occur once every half a millennium. Hurricane Harvey, as many of you will know, brought more than 50 inches of rain over 5 days to parts of Texas in August 2017. And paradoxically enough, droughts are also getting worse. How can you have droughts getting worse and torrential downpours also getting worse? Well, for a number of reasons that are listed here. Higher temperatures mean bigger losses to evaporation between episodes of rainfall. And the fact that more of the rain falls in extreme events means more of it is lost to flood runoff rather than soaking into the soil. The mountains get more rain and less snow, which yields more runoff in winter but less in summer and fall when the droughts take place. Earlier spring snowmelt in a warmer world also leaves less runoff for summer. And in addition, the changes in the global temperature and their uneven distribution is changing atmospheric circulation in ways that are exacerbating drought in some regions. Wildfires, in my view, have been the big sleeper in the early impacts of climate change. Contributing factors to the increase in wildfires, there's a lot of year-to-year variation, but you can see the trend is absolutely unmistakable. Contributing factors to the increase in wildfires are heat, drought, more dead trees killed by pests, and the pests are doing better in a warmer world, so they're killing more trees. You got more tinder for these wildfires, and more lightning. We now understand that lightning is increasing in a warming world, not too shockingly, because the wetter atmosphere contains more energy. When that water condenses, you get thunderstorms, more lightning, and that too is contributing. If you look at what we now know about wildfires, the fire season in the United States is now about 3 months longer than it was 40 years ago. The average fire is much bigger and hotter than before, which means the fires spread faster, they do more damage, they're more dangerous to firefighters. 9 of the 10 biggest U.S. wildfires on record have occurred since 2004. The other one was in 1997. 5 of the 10 largest were in Alaska. Remember, the Arctic is warming faster. And now even the tundra is burning in the Arctic and subarctic. Before, the tundra never burned. It was too moist to burn. Now the tundra is burning, and this picture here is a tundra wildfire in Alaska in the summer of 2015. The other thing we know is that smoke from today's big wildfires can cause health impacts thousands of miles away. This smoke travels enormous distances, it's fine particulate matter, goes in the lung, terrible for health. We know that modest changes in average temperature, and this repeats a point I made in general terms earlier, are leading to enormous changes in heat extremes. And for those of you who have some experience with statistics and what's called the normal distribution, this bump called the Gaussian curve, what happens is you increase the average a little bit, and what happens out at the extreme? The area under the curve in the hot and very hot area goes up enormously when the average changes just a little bit. And that is what we are seeing, the fraction of northern hemisphere land area that is experiencing what used to be 1 in 700-year hot summers has gone up by about 50-fold since the 1950s. Enormous increase in heat waves. This just shows some of the all-time high temperature records that have been set in this year, 2018, and the preceding year, 2017. Again, each one of these temperatures is the highest temperature ever recorded in the indicated location. And you see, even in places that are quite far north, like Scotland, 92 degrees never happened before in Scotland, all the way to 129 degrees in Iran, 128 in Pakistan, and so on. Los Angeles, 111 degrees this month, and so on. Coral bleaching, as the surface layer of the ocean gets warmer, that imposes stresses on corals. They discharge the living algae from the calcium carbonate structure, the superstructure of the reef, and many of those bleaching events are so severe that the coral never recovers. The 2017 bleaching events were the worst ever recorded on the planet, bleaching in many, many parts of the ocean that contained corals, and very problematic. The coral reefs are the second largest reservoir of biodiversity on the planet after the tropical forests. And ironically enough, this is, in a way, an example of Murphy's Law: whatever can go wrong will. The tropical forests and the coral reefs are both differentially at risk. They're particularly at risk from climate change. Oops. Skipped thawing and subsiding permafrost. Picture on the left is Russia, buildings cracking. Picture on the right is from Fairbanks, Alaska, showing the effect on roads, transportation, infrastructure, another big deal. Rising sea level and coastal inundation. This is really a stunning figure if you look at it for a bit. These are the average number of flooding events per year in these different locations in the northeastern United States, all the way down to Washington, D.C. The blue bars at the top are the 50s and 60s. The red bars are the 70s and 80s. The green bars, 1990 to 2009. And the blue bars, 2010 to 2015. Stunning increase in the number of flooding events associated with the combination of rising sea level and very high tides and storm surges. Coastal erosion, an issue on Nantucket and Martha's Vineyard and on the Cape itself. Cape Cod alone loses 33 acres a year to inundation and coastal erosion. Tropical storms. Tropical storms are getting stronger, again, for reasons we understand very well. Tropical storms draw their energy from the warm surface layer of the ocean. It's getting warmer, it's getting deeper, there's more energy to be had. And you see in these indications, in these specific cases, that the largest and strongest tropical storms ever recorded in all these different areas have all occurred since 2012. If you think that's coincidence, I have a bridge in Brooklyn you can have cheap. That is not coincidence. Pest outbreaks, pine bark beetles that have a longer breeding season courtesy of warming end up devastating trees that are already weakened by heat and drought. It's happening in California, Colorado, and Alaska. All these brown trees are trees that were killed by pine bark beetles. Direct impacts on human health: West Nile virus, Lyme disease, malaria, many pathogens and vectors of human disease are sensitive to climate, and many of them do better. The disease organisms and the vectors do better. They breed faster, they bite harder as the climate warms. So what we expect, I've been talking about what we've already observed. This is not theory, it's not modeling, it's observations. What do we expect in the future? Again, I like this particular line, which is attributed both to Yogi Berra and the great physicist Niels Bohr, namely that prediction is difficult, especially about the future. It's not easy. There are significant uncertainties. What's coming depends on the future emissions, and that's indicated here. The key point is that the global average temperature continues to increase under all plausible scenarios. It just increases more the more we emit. If we take drastic action to reduce emissions, we can end up in the lower part of this diagram, the blue curves at the bottom. If we don't take that drastic action, if we proceed along business as usual, we will end up in the red area at the top, leading to temperature increases of 4 degrees C or more above the pre-industrial level. Shown here in a horizontal line is the increase that is targeted under the UN Framework Convention on Climate Change and its conference in Paris, accepted by various international organizations, the OECD, the G20 before that, trying to avoid an increase of more than 2 degrees Celsius above the pre-industrial level. You see we are heading there under all but the blue curves again representing the most energetic and effective efforts to reduce the emissions of the offending gases. And it's quite instructive that the last time the global average surface temperature was 2 degrees C higher than the 1900 level was 130,000 years before the present, and 130,000 years before the present when, as a result of natural influences, the temperature was that high, the sea level was 4 to 6 meters higher than today. Remember, a meter is about 3.3 feet. So 4 to 6 meters is a lot of sea level rise. And that is what we know from the historical record is the equilibrium sea level associated with 2 degrees C increase. This should underline the point that 2 degrees C, the internationally accepted target, is not safe. That just happens to be the lowest increase that the international community could be persuaded was achievable. Now, in Paris, they added a 1.5 degree target because it came to be understood that 2 degrees was already potentially devastating in many respects. We're already experiencing the severe effects that I listed before at 1 degree C. And we think 2 degrees C is safe? It's not. The issue, in part, is the momentum in the climate system. That momentum in the climate system means that the temperature continues to go up even after the atmospheric concentrations of these heat-trapping substances stabilize, and sea level continues to go up even after the temperature stabilizes. The only question is how fast the sea level will go up. And this shows, this is a NOAA analysis, that sea level is likely to rise another 0.5 to 2 meters by 2100. Again, the 2 meter possibility is under high emissions, the 0.5 meter possibility under much lower emissions. But again, sea level continues to rise for many centuries after 2100. This graph is just through 2100, and ultimately will reach 2 meters or more per degree of global average warming. I live in Falmouth, by the way. Sherry and I live in Falmouth. A foot of sea level rise would turn Woods Hole, one of the villages in Falmouth, into a set of islands. A foot would do that, and we are heading there. This shows the areas of the East Coast that would be flooded with 1 meter of sea level rise, the red. You see the amount of red on Cape Cod, the amount of red on the islands of Martha's Vineyard and Nantucket, the amount of red all the way down the East Coast. A 1 meter would be a stunning impact on the northeastern United States, including the Cape and Islands. We would expect heat waves, which have already increased drastically, to increase much more. The scale here is a little hard to read, but it tells you by what multiple heat waves are expected to increase under a business as usual scenario, comparing the period 2040 to 2070 against the period 1970 to 2000. And the darkest color represents a 6-fold increase in the incidence of heat waves. 6 times more heat waves in much of the United States. Wildfires, even a 2 C increase, the target, portends a large worsening of wildfires. These percentages show the increase in median annual area burned compared to the 1950 to 2003 average for a 1 C rise in global average temperature. You look at some of these percentages, 300, 400, nearly 500%, some over 500% increases in the average annual area burned in the western United States. All scenarios involve increased storminess. These are just the titles and the sources of some of the recent publications on the connections between storminess and the warming in which we are currently engaged. Probably the best hurricane model in existence is the model at the Princeton Geophysical Fluid Dynamics Lab. It projects an increase in landfalling Category 3 to 5 hurricanes in the northeastern United States under a medium emission scenario. This shows the increases extending all the way up to Maine of landfalling hurricanes expected under these emissions and temperature scenarios. Impacts on northeastern fisheries. We're already seeing the lobsters move north, the impact on the Gulf of Maine cod fishery. An assessment of the vulnerability in the northeast fisheries going forward says that basically climate vulnerability is high to very high for about half of all the species assessed in the Northeast. And again, this is work that was done by the NOAA Northeast Fisheries Science Laboratory in Woods Hole. A lot of other impacts likely to affect the Cape and Islands. Saltwater intrusion into freshwater wetlands and aquifers, which is made worse by increasing groundwater pumping to serve growing populations in this region. We expect more frequent, more intense, and longer red tides with associated shellfishing closures. We expect additional threats to lobsters and mollusks from bacterial and other diseases that flourish in warm water, more damage to native marine species by invasive species from warmer regions, reduced abundance of northeast bird species, and diminution of cranberry production. So what can we do? Again, a nice quote, if you don't change direction, you'll end up where you're heading. What can we do? We only have 3 options in the face of the climate change challenge. One is mitigation, the measures we take to reduce the pace and magnitude of the changes in global climate that we're causing. The second is adaptation, meaning measures to reduce the adverse impacts on human well-being that result from the changes in climate that do occur. And the third option is suffering the adverse impacts and the societal disruption that we fail to avoid by the combination of our efforts in mitigation and adaptation. The truth, of course, is we're already doing some of each. We're doing some mitigation, we're doing some adaptation, and as we've seen, we're doing some suffering. What's up for grabs, what's at stake going forward is the future mix of those. How much mitigation, how much adaptation, how much suffering. And minimizing the amount of suffering in that mix, which should, of course, be our goal, can only be achieved by doing a lot of both mitigation and adaptation. Mitigation alone won't work because climate change is, as we've seen, already occurring, and it can't be stopped in its tracks. It can't be stopped quickly, no matter what we do, because of the momentum in the climate system, and by the way, also the momentum in human practices. We can't change them overnight. Adaptation alone won't work because adaptation gets costlier, less effective, more difficult as the changes in climate to which you're trying to adapt get bigger. So we need enough mitigation to avoid unmanageable climate change and enough adaptation to manage unavoidable climate change. A lot of ways to do mitigation: reducing the emissions of greenhouse gases and black soot from the energy sector, reducing deforestation, increasing reforestation and afforestation, modifying agricultural practices to reduce emissions of greenhouse gases and build up the carbon stored in the soil. Conceivably, we might learn to scrub greenhouse gases from the atmosphere technologically basically artificial trees. We might resort to geoengineering to create cooling effects, offsetting greenhouse heating, although we would need to be very careful to be sure the unintended side effects of that are not worse than the disease. How much do we need? Well, again, 2 degrees C above pre-industrial, now considered by many the most prudent target that's still attainable, embraced long ago by the European Union, more recently by the G8 and the G20, reinforced in Paris in 2015. Paris added this aspirational goal of 1.5, although it's very hard to see how we could get there. To have just a 50% chance of staying below 2 degrees, we would have to stabilize the atmospheric concentration of heat-trapping substances at the equivalent of about 450 parts per million of CO2. We're already over 400, by the way. In order to reach that target, developed country emissions, industrial country emissions, really needed to peak a couple of years ago, and they need to be declining rapidly. And developing country emissions must peak no later than 2025 and decline rapidly after that. The question arises, is that even affordable? Could we afford to pay for that? Well, detailed analysis by the McKinsey Group says that if you just had a carbon tax that increased over time to $70 a ton of carbon dioxide equivalent by 2030, that would put the world on a trajectory to get to 2 degrees C. The total tax bill under that circumstance would reach about $2 trillion a year in 2030, but that's not society's cost, because the average cost to reduce those emissions would be much less than $70 a ton. The $70 is what it cost to get the last ton, but the earlier tons are cheaper. And governments could rebate that tax on a per capita basis, which would make it progressive rather than regressive. That's what the state of Alaska does with its oil royalties, rebates them on a per capita basis to the citizenry. Furthermore, gross world product in 2030 at 2.5% per year growth between now and then would be $170 trillion. So even the $2 trillion figure would only be around 1% of world economic product. And the world now spends 2% of its economic product on defense. That is twice as much as it would cost us in the most pessimistic assumption to address the climate change issue. We in the United States spend 3.5% of our GDP on defense. We spend 1.7% on environmental protection already. And these costs, this is very important, these costs are not losses. They're just choices about resource allocation. Spending the money to achieve these things creates jobs, it supports businesses, and so on. Most economic models find that all the way out to 2100, the aggressive mitigation we need would reduce world economic product by 2 to 3% in 2100. But we understand all of those models underestimate innovation over the long run. Innovation is already making this cheaper. And of course, you have to ask the question, compared to what? Far less affordable would be paying the costs of unmitigated climate change. There's the damage to the world economy if we fail to mitigate climate change will be much larger than the costs of fixing it. Adaptation possibilities, there are a lot of them. They're listed, some of them here. Again, I won't read this list to you in the interest of time, but I will note that many of these approaches are what we call win-win approaches. They would make sense even if climate weren't changing. After all, there have always been powerful storms. There have always been floods, there have always been droughts and wildfires. We've always been underprepared. Investing more in preparedness and resilience and adaptation would be a bargain even if the climate weren't changing. It's just a bigger bargain because the climate is changing. Need for and current lack of federal leadership. In the Obama administration, we boosted climate change research and monitoring. We invested in clean energy research and development incentives for that, incentives for the private sector to do more, like making the research and experimentation tax credit permanent. It took us 5 years to do that. We got it done. We promoted aggressive energy efficiency standards. We promoted climate change adaptation with a huge array of executive orders and changes in government policies. We launched the Climate Action Plan in June of 2013 with further mitigation, adaptation, and international initiatives. We reached agreement with China in November 2014, which really enabled the Paris Accords with 195 countries to succeed in December of 2015. But the Trump administration has taken a different course. It's put climate change contrarians in charge at the Office of Management and Budget, the Environmental Protection Agency, the Department of Interior, and the Department of Energy, left many key science positions unfilled. We still don't have a successor to me. There is no science advisor, no OSTP director in the Trump administration. The Trump administration has proposed deep budget cuts in both climate science and clean energy R&D. And President Trump has canceled Obama's climate action plan, and virtually every executive order that Obama issued on climate change, mitigation, and adaptation has been canceled by President Trump. And of course, as we all know, President Trump withdrew from the Paris Accords. The damage from those steps is significant, but it's also limited. First of all, the United States cannot formally withdraw from the Paris Accord until 2020. But what Trump has done is to halt most of the federal government's efforts to comply with the Paris Agreement. The most damaging potential consequences are loss of U.S. credibility and moral authority in the global community, cuts to government-funded climate research, Earth observation, and energy research and development. Congress has to accept those proposals. Up until now, they haven't accepted all of them, but they've accepted some of them. That damage is hard to reverse. Elimination of federal government standards affecting U.S. emissions. Cuts to U.S. climate change assistance to other countries. It's a very hard one to reverse in the sense that the lack of those funds for a period of time sets back progress no matter what you do afterwards. But it is important to note that many states, cities, companies, universities, civil society organizations, and individuals in the United States are taking positive steps to meet Paris commitments by this country. Many Americans are part of what's called America's Pledge, the We're Still In movement. That is, the federal government may be out of Paris or aiming to be out of Paris, but a lot of folks are still in. Those folks include the state officials in more than 20 states. They include city officials in hundreds of cities. They now include CEOs in more than 1,000 U.S. corporations. Business Backs Low Carbon USA has more than 1,000 companies in it. More than 600 CEOs, by the way, wrote President Trump ahead of his Paris withdrawal, said, please don't withdraw. It will be bad for business to withdraw, not good for business. But let's turn to what individuals should do. Climate scientists should continue, obviously, their work to monitor climate change and its impacts, to improve projections of future conditions, which we need for states and localities to adapt. And they should continue to communicate to both decision makers and the public, not only what we know, but how we know it. Business people should embrace the private sector movement to reduce their companies' emissions, should build their resilience against climate change impacts, should invest in energy innovation. Civil society leaders should use the influence of their organizations to propagate understanding of climate change impacts and the remedies that are out there. State and local government officials should be creative in advancing those remedies. Philanthropists should support all of those efforts, starting with filling the gaps led by the federal government's retreat. And finally, what everybody should do. Here's my list of what everybody should do. I'll just run through these very quickly, and you can read them. Can people read these in the back? Good. All right. And last, and certainly not least, vote, and even better, work for political candidates who understand the change and pledge to act. Trend is not destiny. Thank you very much. I don't know if we have time for questions. What's the verdict on that? Yeah, I think we have time for questions. Right up here. First one.
Could you tell us what technology you see in front of us which will help to curb the trend, like for example, electric driving, which is popular in Europe and
Yeah.
on the West Coast. But I mean, are there things which you see coming which will counter?
Well, there are a lot of things coming both on the demand side and on the supply side. Let me mention very briefly on the supply side, the costs of both wind and solar energy have been rapidly falling. Their use has been rapidly growing in the United States and around the world. Over the course of the Obama administration, from 2008 to 2016, you just compare those numbers, the year 2008, the year 2016, solar electricity generation in the United States went up more than 40-fold. Wind energy generation in the United States went up more than 4-fold. And that was because the prices of those had fallen so that in many parts of the country they were competitive with conventional energy sources. The opportunities on the technology side do include electric vehicles. Electric vehicle sales are going up. The technology is getting better. Batteries are getting better. The next generation of electric cars will probably have a range of 250 miles and the capacity to be recharged in 10 minutes rather than 30. The potential for reducing the energy use needed to make a ton of steel, a ton of aluminum, a ton of plastics, all of that is falling. That is, the processes are getting more efficient. LED bulbs have absolutely transformed the lighting business, drastically lower consumption of electricity for lighting. Even in car headlights, you need to generate less with your car's generator or alternator just to run your headlights because LEDs are so much more efficient. There's some other technologies that will need further development before they start to have an impact. One of those is carbon capture and sequestration. That is, when you do burn fossil fuel, rather than releasing all the carbon dioxide into the atmosphere, capturing most of it out of the exhaust gas and sequestering it in geologic formations where it will stay for thousands of years. That's currently too expensive to be competitive, but we basically know how to do it, and it's a matter of reducing the costs. Nuclear energy, which was mentioned in the introduction, could play a big role if we can overcome its challenges. Right now, nuclear energy is too expensive. It's much more expensive than natural gas. It's more expensive than wind and solar. We should be trying to fix that, and we should be trying to solve the problems of radioactive waste management, the protection of weapon-usable material in civil nuclear fuel cycles. We need to make the reactors safer at the same time we're making them cheaper. I believe those problems can be solved. Whether we're actually smart enough and wise enough to do it is an open question. If we don't get that contribution from nuclear and maybe considerably later from nuclear fusion as well as nuclear fission, we will just have to get all the more from renewables, from efficiency, from carbon capture and sequestration. And those are some of the possibilities. Yes, way in the back. Yeah, the question, if you didn't all hear it, was talk about the challenges of population growth. Paul Ehrlich and I wrote a paper in 1971 that pointed out that impact on the environment is a product of three factors: the number of people, the amount of economic activity per person, and the amount of environmental impact per dollar of economic activity. And that is what's called an identity. It's not controversial. It can't be controversial because it is identically true. The factors are all three important, as we pointed out in this 1971 paper. You can't say any one factor is unimportant because each multiplies the other. I was involved in an international study for the UN Secretary General that came out in 2007 that actually calculated the leverage in each factor going forward. And again, you see that they're all important. If you have fewer people, it is easier to reach any given target than if you have more people. Whatever you do in terms of affluence, consumption per person, and impact per unit of consumption, fewer people means lower impact. Population limitation is, of course, a controversial topic. The good news is that what we have learned about limiting populations over the last 40 or 50 years is that the single most important factor in reducing population growth is empowering women, educating women, giving them opportunities, giving them access to health care, giving them access to contraception. And it turns out that people generally have for a long time been wanting fewer children than they've been having on a global average. And when you make it possible for people to have the number of children they want, the rate of population growth goes down. It's gone down drastically in most of the industrialized nations, in the United States, in Europe, Japan. It has been coming down in the developing countries, and we could make that happen even faster, most easily, by expanding the opportunities for women, education, employment opportunities, access to health care around the world. Yes, in the middle here.
Are you surprised at how easy it's been for the Trump administration to reverse all those policies?
So if you didn't all hear that, am I surprised about how easy it has been for the Trump administration to reverse those policies? Short answer is yes, I have been surprised. You know, it's a standard insight that presidents come into power expecting to change things drastically, and invariably they find it harder to change than they expected, in part because of the public servants who are entrenched in all the governmental agencies who continue to try to do their jobs even though there's a different president. But Trump has been more effective at overcoming that than I think any of us really expected. And part of the problem was that in the Obama administration, we did not, for the last 6 of the 8 years, have any support from the Congress on anything, but we did manage to increase clean energy research and development during that period. We only managed to hold the line on climate change research, on climate change monitoring, and so on. And not having the support of the Congress meant that we had to use executive authority. That's why we had all these executive orders. And that's why we had tightening efficiency standards on appliances and buildings and tighter fuel economy standards. All that could be done with executive authority. But unfortunately, what is done with executive authority can be undone by executive authority, at least much of it. Now, some of what Trump is trying to do in the way of retreating from these measures is being challenged in the courts. And I think he will not win in all cases. But again, there's a fair amount of damage being done, including damage that will be hard to reverse because we had to do so much of it with executive authority, and that stuff is vulnerable. Over here.
Is there a relationship between economic growth and population growth? And if there is, would then be trying to create reduction in economic growth?
Well, actually, the correlation between economic growth and population growth is an inverse correlation. That is, as people get richer, they tend to have smaller families. And so it has long been argued that part of the solution to the population challenge is to make everybody richer faster. And I think folks, most nations have accepted that. And most of the industrial nations make substantial contributions to development efforts in the less developed world. Trump is backing off from that as well, reducing assistance to developing countries in many different forms. But of course, there's a bit of a catch-22 there because you make people richer, they consume more, and so the populations aren't growing as fast, but that consumption factor is going up. And then what you find yourself doing, you say, well, we have to rely on better technology. And even a lot of the folks who have been questioning the urgency of the climate change problem are, in principle, in their rhetoric at least, saying we're willing to invest in advanced technology as the solution to this. What we have to do is we have to compensate for the combination of population growth and growth in consumption by making that technology factor smaller, by cleaning up our technology so that the emissions per dollar of economic activity go down. But again, the irony is a lot of the folks who talk that talk are not walking the walk. They are not voting in Congress to increase expenditures on improving the technologies. And you can't really have it both ways. You can't say we can deal with whatever population and average per capita consumption we end up with better technology if you're not willing to pay for getting the better technology. Right now, in the United States, we spend about 2.7% of GDP on research and development. That's private and public combined, 2.7%. We had a goal in the Obama administration of getting to 3%. We didn't get there because the Congress wouldn't help us. But 3% is also not enough. How do we know it's not enough? You know, people sometimes say, well, the really tough question in supporting R&D is figuring out how much is enough. We know it's not enough because the pace of progress is too slow. We are not reducing emissions fast enough. We're not increasing energy efficiency fast enough. We're not improving manufacturing processes fast enough to grapple effectively with the challenge that we face. We look at the pace of climate change. We look at what we need to do to it. We need to innovate faster. It's interesting, I gave this speech so often for so long that when my grandson, who's now 17, was 4 years old, I came back from one of my speeches, he said, "Grandpa, we have to innovate faster." And it's true. But if you're going to innovate faster, you have to pay for it. And by the way, you have to be willing to invest in outside the box ideas. You have to be willing to try things and fail. One of the problems with federal R&D is that anytime a project fails, the Congress tends to blame the Department of Energy or NOAA or NASA, whatever agency it was whose project failed. And the fact is, if some of your projects don't fail, you're not trying hard enough. You're not doing enough experimentation. You have to think about R&D as a portfolio, recognizing you're going to try a lot of things, and if a few of them wildly succeed, you will succeed as a society. And that's what we should be doing. We should be making more bets. We should be doing more outside the box investments in energy supply and energy efficiency and manufacturing and infrastructure. And at the moment, we're not doing enough. Oh, we got lots of questions right down here.
Okay, so speaking to this audience, you're preaching to the choir, pretty much. There's plenty of places, by no means the majority, but plenty of places if you came and gave the same presentation, you might actually get some booze from the...
I've done that.
So do you have any, especially since you've had that experience, do you have any particular thoughts as to how to get through the, I think most important single thing is human causation, to get understanding and agreement and support from that? Any angles that you...
Well, one of the angles is you can't just talk, you have to listen. You have to listen to what people are saying about what they think and why they think it. And then you have to address those concerns, those thoughts in an agreeable manner. That is, you don't say, "You're obviously an idiot." You say, "Well, I have a slightly different view. Here's what I think about it and why. And what do you think about my answer?" I spent a lot of time talking to various groups of members of Congress, including a lot of Republican groups, and I got some very strong disagreements, but I also changed some minds. I have given talks on this subject in North Dakota and in Georgia and in Virginia and a lot of other places that are, let us say, less progressive on these matters than Nantucket or Woods Hole. And it's a very good question. I mean, basically, the trick is not to belittle people, not to tell them they're idiots, but to figure out what it is that is troubling them about accepting the scientific consensus on this. Very often they know what the scientific consensus is, they just don't accept it. Some of them don't know what it is, but some of them know what it is and don't accept it. And sometimes the reasons are very interesting. For example, a lot of Republicans in the Congress know in their hearts that the science is right, but they are arguing that it isn't because they fear that if the public accepts what scientists are saying about climate change, the public will embrace a regulatory regime which goes against everything that Republicans believe. And in fact, a very well-known Republican strategist named Frank Luntz wrote a memo to the Republican leadership to that effect in 2000, and it leaked ultimately. And it became known that what Luntz said in this memo is what I just said. He said, Republicans have to attack climate science because if the public ever accepts it, they'll accept regulations which we Republicans will hate. So one of the things you have to explain is that there are a lot of ways to address climate change that will make money, that will use economic markets, that will benefit business, that will benefit per capita well-being. And of course, we have to be smart about what approaches we as a society take to get our arms around this problem and fix it. It doesn't have to be all regulation. People start to listen. I did succeed in persuading a number of very prominent Republican members of Congress using those kinds of arguments. And we would have had a great deal more cooperation had it not been for the degree of politicization that had taken place around this issue, the degree of polarization between Republicans and Democrats that basically during the Obama administration made cooperation anathema to many of the folks in Congress. I mean, if Obama was for it, a lot of the Republicans were against it, even if what he was for was something that Republicans previously favored. And we got to get past that in this country. We got to get back to the place where Republicans and Democrats can discuss their differences and figure out what kinds of policies will enable the country to move forward together. Yes?
I just have a question. You made obviously major arguments for climate change, but you began your presentation with saying that before climate change we were going through a cooling trend. What were the forces that caused that cooling trend, and what would have happened if we had not screwed things up?
Well, the main forces that have caused natural climate change over the millennia, including the onset of ice ages and then the end of ice ages, are perturbations in the Earth's orbit and the tilt of its axis, and what's called the precession of the axis of rotation of the Earth. A rotation like a top starts to rotate as it starts to run down. Those changes, when they were in synchrony to cause more sunlight to fall, for example, on the northern hemisphere, that tended to move us out of cold spells. And when those changes were in synchrony to cause less sunlight to fall on the northern hemisphere, they brought us into ice ages. And those forces, those what are sometimes called the wobbles in the Earth's orbit and its axis of rotation, were, while small, when acting over hundreds and thousands of years and amplified by what are called feedbacks. As the Earth starts to get warmer, it drives more carbon dioxide out of the ocean and out of the soil. When it gets colder, more goes back in the ocean. That's what has driven all the cycles for many millennia, the beginnings and endings of ice ages, and they were taking us toward another ice age. We would have had, if humans weren't doing what they've been doing since the Industrial Revolution, we probably would be in another ice age 10,000 years from now. It takes a long time, many thousands of years. So some of the members of Congress who said, while I was testifying before them, that the explanation for what we were seeing was not human activities. The explanation for the current warming was, one of them said, the wobbles. He was exactly wrong. The wobbles had been taking us in the other direction, but we overcame them with our emissions of heat-trapping substances. And you can say that's a great thing. It would be terrible if we had another ice age in 10,000 years. But what we've gotten in exchange is an extraordinary rate of heating on a time scale of decades. Let's see, back there, yeah.
How serious is China about climate change?
China is very serious about climate change. I've been going to China since 1984 and meeting with Chinese leaders about a variety of global issues. We've been talking extensively about climate change with the Chinese since the late 80s, early 90s. For a long time, their rhetoric publicly was very different from what their scientists and their decision makers were willing to say privately. Their rhetoric for a very long time was climate change is a problem that the industrialized nations caused with their emissions. The industrialized nations are going to have to fix it. if they want us to participate, they're going to have to pay us. That was their rhetoric for a very long time. That rhetoric started to change in the 2000s, but they were already talking privately with me and others who were going and meeting with them privately in a more sensible way for some years before that. And now they are very public in their acceptance that climate is changing, humans are causing it. It's already doing significant damage in China. China is experiencing the droughts, the floods, the heat waves, the reductions in crop production that have gone with that. Of course, they have a situation in which their very serious conventional pollution, the particulate matter and the oxides of sulfur and the oxides of nitrogen that are making the air practically unbreathable in major Chinese cities, the things you need to do to fix that are very often the same things you need to do to reduce the emissions of heat-trapping gases. And so the Chinese, again, have a win-win. They want to address both problems. They're taking steps to make progress on both problems. They're going to beat their Paris commitments. We're not going to beat ours. It's kind of embarrassing. The Chinese president, Xi Jinping, and President Obama in November of 2014 in Beijing stood up together and said, we're the two biggest economies, we're the two biggest emitters. We both recognize climate change as a surpassing challenge of the 21st century, and both of our countries are prepared to lead in the efforts to address it. And it was that agreement by the two presidents in public that really made the difference in the whole global discussion of climate change and climate policy and made the Paris Accords possible. And we're now in this position where the United States has, in a way, voluntarily, at the level of the President of the United States, conceded the global leadership on this issue to the Chinese. Chinese are still there. The Chinese are still doing all the things they said they would do. If you were to be parachuted in to the electric vehicle lab at Tsinghua University, the MIT of China, or the biofuels lab, or the energy efficiency lab, you would not know that you hadn't been parachuted into MIT or Princeton or Stanford or Chicago. Their facilities are as good as ours, in some cases better. Their investments are going to pass ours very shortly in these domains. They're very serious, and we should get back to being serious too. I think I'm being told we're done. One more. Well, let's see. Here we have. You're going to ask your husband's question.
Yes. Says it's clear the world is warming faster than most climate experts thought just a few years ago. How much faster do you think oceans can rise than projected by 2050?
Well, the problem with that, it's a very good question, but the biggest uncertainty about the future of climate change is not the uncertainty in the models. It's not that our understanding of the atmosphere or the ocean is imperfect. It is imperfect, but it's pretty darn good. The biggest uncertainty is in what society chooses to do. The biggest uncertainty in how much sea level will go up in this century is whether we're on a high emissions trajectory or a low emissions trajectory. And that's a very big difference. So what do I think it's going to be in 2050? I think if we don't get our act together, sea level in 2050 could already be 1 meter higher than today, 3.3 feet. And you're going to be looking at Woods Hole is now a bunch of islands rather than one village. On the other hand, if we get our act together, the amount of increase by 2050 might be a foot or a foot and a half. That will still cause a lot of damage, by the way. We cannot get out from under the fact that there's going to be more damage, but we can affect how much more by the actions we take. And that's really the message I want to leave with all of you. It really is up to us, all of us, how much damage there's going to be. For us, for our children, for our grandchildren, we've got to get our act together, and we've got to get it together quickly. Thank you very much.